Imagine tapping the screen of your phone. You barely touch the glass and somehow the phone knows exactly where your finger landed. Not just that you touched it. It knows whether you tapped an icon, dragged something across the screen, scrolled through a page, or used two fingers to zoom in. And it can detect all of this almost instantly. But there isn't a tiny camera underneath the glass watching your finger. There isn't a physical button hiding beneath every part of the display. Instead, beneath that smooth surface is an invisible electrical system constantly measuring what's happening around it. The moment your finger touches the screen, you disturb that system. Your phone detects the change, calculates exactly where it happened, and turns that information into the action you see on the display. So how can a sheet of glass detect your finger? And how does a simple touch become a command almost instantly? A smartphone screen might look like one simple sheet of glass, but underneath that surface is a carefully constructed stack of different layers. The glass you touch is mainly there to protect everything underneath. Below it is a transparent layer designed to detect touch. And underneath that is the actual display, made of millions of tiny pixels that create the images, colors, and text you see. Beneath all of that are the electronics responsible for controlling both the display and the touch system. The exact construction varies between devices, but the important part is this. The layer that detects your finger has to be transparent enough for you to see the display underneath it, while also being electrically conductive enough to detect changes caused by your touch. To accomplish this, manufacturers use extremely thin conductive materials arranged across the screen. These conductive elements form a microscopic grid. You can't see this grid when you are using your phone because the individual elements are incredibly small and designed to let light pass through. But your phone's electronics can monitor what happens across that grid. Think of it like turning the entire screen into thousands of tiny invisible detection zones. The phone doesn't have to watch your finger with a camera. Instead, it is constantly checking the electrical conditions across the surface. When everything is normal, the system knows what the screen's electrical state should look like. Then your finger touches the glass. Something changes. And that change is what the touchscreen is actually looking for. Because your finger isn't just a piece of skin. Electrically speaking, it's part of the system. Your finger might seem like an ordinary object, but electrically, it's surprisingly useful. The human body contains a large amount of water, along with dissolved salts and other substances that allow electrical charge to move through it. That makes your body conductive. And capacitive touchscreens take advantage of this property. But here's an important detail. Your phone isn't simply sending electricity through your finger and waiting for it to come back. Instead, the touchscreen creates a tiny electrical environment across its surface. When your finger gets close to or touches the glass, your body interacts with that electrical environment. The electrical properties at that particular spot change. Think of it like dropping your finger into a perfectly organized invisible pattern. Before you touch the screen, everything is behaving normally. Then your finger arrives and the electrical conditions around that point shift. The touchscreen controller notices that change. This is the basic principle behind capacitive touch. The word capacitive comes from capacitance, which describes how much electrical charge can be stored in a system under particular conditions. You don't need to understand all the mathematics behind capacitance to understand what your phone is doing. The important idea is simple. The screen establishes an electrical pattern. Your finger changes that pattern. The phone measures the change. And from those measurements, it can determine where you touch. But the really impressive part is that the phone isn't checking just one spot. It's monitoring an entire grid across the screen. That means your finger can touch almost anywhere, and the system can figure out which part of the grid was affected. And because the electronics can scan this grid incredibly quickly, the phone can continuously follow your finger as it moves. That's how a touch screen can detect much more than a single tap. But how does the phone turn that tiny electrical disturbance into an exact location on the screen? The touchscreen doesn't need to know exactly what your finger looks like. It only needs to know where the electrical change happened. Under the glass, the conductive layer is arranged in a grid of intersecting lines. You can imagine it like a giant invisible coordinate system spread across the entire screen. The horizontal lines help establish one dimension. The vertical lines establish the other. Together, they allow the touchscreen controller to determine an X and Y position. When your finger touches the screen, it changes the electrical characteristics around a small area of that grid. The controller rapidly scans the grid, looking for these changes. Suppose you tap an icon near the upper right corner. The controller detects a change in that region and converts it into coordinates. It might effectively determine something like X equals 850, Y equals 420. Those numbers aren't the important part. What's important is that the touchscreen has transformed a physical touch into a location that the phone's computer can understand. And this happens extremely quickly. The controller continuously repeats the process, checking the screen again and again. So if you move your finger across the glass, it doesn't just detect where you started. It detects where you are now, then where you move next, then where you move after that. The result is a constantly updating stream of coordinates. And once the phone knows those coordinates, the touchscreen hardware has done its part. But the phone still has to figure out what those coordinates mean. Because touching the top right corner of the screen doesn't automatically mean open this app. That's where software takes over. Your phone now knows something very specific, where your finger is. But coordinates alone don't tell the phone what you want. Imagine you tap an app icon. The touchscreen controller detects the electrical change and sends the location of that touch to the phone's operating system. The software then looks at the screen and asks a simple question. What is located at these coordinates? If those coordinates fall inside the boundaries of an app icon, the phone knows that you probably meant to select it. So the process looks something like this. Finger touches, screen right arrow, electrical change right arrow, coordinates right arrow, software interprets the coordinates right arrow action. And because all of this happens incredibly quickly, it feels completely instantaneous. But there's another important part. The phone doesn't only record where you touch. It also records when you touched, how long you stayed there, and whether your finger moved afterward. That's how the same physical contact can produce completely different actions. A quick touch followed by a release can be interpreted as a tap. Hold your finger in one place, and the phone can recognize a long press. Move your finger while maintaining contact, and the phone can interpret that as dragging. So the touchscreen hardware is essentially providing raw information about your finger's movement. The operating system turns that information into meaning. It's similar to giving a computer a series of coordinates on a map. The coordinates themselves don't tell you what the person is doing. But if you watch those coordinates change over time, a pattern begins to appear. And that's exactly what your phone is doing with your finger. It's constantly collecting tiny pieces of information and looking for patterns. Which means your phone doesn't need a separate mechanism for every possible gesture. It can use the same basic touch detection system to recognize dozens of different interactions. But this raises another question. If the touchscreen is constantly detecting where your finger is, how can it tell the difference between a tap and a swipe? The answer is movement over time. A tap and a swipe can begin in exactly the same way. Your finger touches the screen. At that first moment, the phone simply knows where the contact happened. The difference comes from what happens next. Imagine you touch the screen and immediately lift your finger. The phone sees a very short sequence. Touch right arrow, stay almost still, right arrow, release. The software recognizes that pattern as a tap. Now imagine you touch the screen and keep your finger on the glass while moving it to the side. The touchscreen controller detects a constantly changing stream of coordinates. Touch right arrow, position changes, right arrow, position changes, again right arrow, release. The software recognizes that movement as a swipe. The same principle works for dragging. Suppose you press and hold an icon, then move your finger across the screen. The touchscreen keeps reporting your changing position while your finger remains in contact. The operating system can interpret that as start here, keep holding, follow the movement, release here. And scrolling works in a similar way. When you swipe upward on a web page, your phone doesn't physically move the web page upward because your finger touched it. Instead, the touchscreen reports the movement of your finger. The software interprets that movement as a scrolling gesture and moves the content on the display. This is why the touchscreen hardware and software have to work together. The hardware is responsible for detecting the physical interaction and providing information about it. The software is responsible for deciding what that interaction means. And because the screen is being scanned repeatedly, the phone can follow your finger's movement closely enough to make the interaction feel continuous. But there's an even more impressive trick. Your phone doesn't necessarily have to choose between detecting one finger or another. It can track several fingers at the same time. That's what makes multi-touch possible. Now put two fingers on the screen at the same time. You can spread them apart to zoom into a photo, bring them together to zoom out, or use several fingers for different controls in a game. So how does the screen know that these aren't just one giant touch? The secret is the touchscreen's grid. When one finger touches the screen, it changes the electrical conditions in one area of that grid. When a second finger touches somewhere else, it creates another change in a different area. The touchscreen controller can detect these separate changes and determine that there are multiple points of contact. It can then track each point independently. For example, imagine placing your thumb and index finger on a photo. At first, the phone might detect point 1 right arrow x1, y1, point 2 right arrow x2, y2. Then you move your fingers apart. The phone continuously updates both positions. The software notices that the distance between those 2 points is increasing. It recognizes the pattern as a pinch-out gesture and enlarges the image. Move them toward each other and the distance decreases. The software interprets that as a pinch-in gesture and zooms back out. The touchscreen isn't actually thinking, "This person wants to zoom." It's simply reporting what your fingers are doing. The software does the interpretation. This same principle allows phones to recognize multiple touches in games, scrolling gestures, drawing, and many other interactions. And the technology can track more than 2 fingers. Depending on the device and software, several points can be detected simultaneously. That's pretty remarkable when you think about what's happening. There's no tiny mechanical switch underneath each fingertip. There's no camera following every finger. The screen is essentially measuring tiny electrical changes across an invisible grid and continuously turning them into coordinates. But if your finger is what creates that electrical change, something interesting happens. What if you aren't touching the screen with your bare finger? Why doesn't a normal plastic object always work? And why can a special stylus work perfectly? Not every object can interact with a capacitive touchscreen the way your finger does. Try tapping a modern phone with an ordinary plastic pen. Usually, nothing happens. That's because plastic doesn't interact with the touchscreen's electrical field in the same way your body does. Your finger is conductive enough to change the electrical conditions around the screen. A plastic pen generally isn't. This is also why a regular glove can sometimes prevent a touchscreen from responding. The material between your finger and the glass can stop your body from interacting strongly enough with the touchscreen's sensing system. But that's why some gloves are specifically designed to work with touchscreens. They use conductive material in the fingertips, allowing the electrical interaction to reach the screen. And then there are styluses. A simple capacitive stylus can use a conductive tip that behaves somewhat like your finger. But more advanced styluses can do much more. Some are designed to communicate with a specialized sensing system in the screen, allowing the device to detect the stylus with much greater precision. Depending on the technology, the device can determine things like the stylus's position, movement, and sometimes even pressure or orientation. This is especially useful for drawing and handwriting. But the basic idea remains the same. The touchscreen needs some way to detect a change in its electrical environment. Your finger naturally provides that. A conductive stylus can imitate it. A specialized digital pen can use additional technology to communicate with the device. And this also explains why your touchscreen can sometimes behave strangely. Because the phone is constantly measuring extremely small electrical changes, anything that unexpectedly changes those conditions can potentially interfere with the system. A wet screen is a good example. Water can spread across the surface and create electrical effects that weren't caused by your finger. Suddenly, the touchscreen may detect touches where you never intended to touch. And that's when you start seeing one of the most annoying touchscreen problems: ghost touches. A touchscreen is constantly trying to separate intentional touches from everything else happening on its surface. And sometimes that isn't easy. Take water. If a few drops land on your screen, they can alter the electrical conditions across the touch-sensitive layer. The phone may detect those changes as if something touched the screen. That's why a wet touchscreen can sometimes start opening things, scrolling, or reacting in ways you never intended. Dirt and oils can also interfere with the surface. And then there are screen protectors. A properly designed protector usually works without any problem, but a damaged, poorly fitted, or unusually thick one can sometimes affect how accurately the touchscreen detects your finger. Even your own fingers can create unexpected inputs. If your palm or another finger accidentally touches the screen while you're holding the phone, the touchscreen may detect it as another point of contact. Fortunately, the software is designed to recognize many of these situations and ignore touches that don't make sense. But it can't always tell perfectly. After all, the touchscreen doesn't actually know what you're trying to do. It only knows what its sensors are detecting. That's the fascinating part. Your phone isn't looking at your finger and thinking, "That's a finger." It's measuring electrical changes and sending that information to software. The software then tries to make sense of those measurements. A single stationary point might be a tap. A point that moves across the screen might be a swipe. 2 points moving apart might be a zoom gesture. A strange collection of rapidly changing points might be accidental input. And all of this happens in fractions of a second. So when you tap your phone, there are actually several different systems working together. The touchscreen detects the physical interaction. The controller converts that interaction into coordinates. The operating system interprets those coordinates as a gesture. And finally, the software decides what should happen on the display. What feels like one simple action is actually a chain of incredibly fast measurements and decisions. And once you understand that, the touchscreen starts to look very different. Because what appears to be an ordinary sheet of glass is actually an invisible electrical grid constantly sensing the world around it. And that brings us back to the simple action we started with. You tap a screen and something happens. But underneath that tap is an entire chain of technology working almost invisibly. Your finger changes the electrical conditions at the surface. A microscopic grid detects that change. A touchscreen controller determines where it happened. The phone converts that information into coordinates. Then the software looks at those coordinates, watches how they change over time, and figures out what you're trying to do. A quick touch becomes a tap. A continuous movement becomes a swipe. 2 moving points can become a pinch to zoom gesture. And all of it happens so quickly that you experience it as one seamless interaction. The screen isn't actually seeing your finger. It's not physically detecting your fingertip like a button would. It's sensing how your finger changes an invisible electrical system beneath the glass. And that's what makes the technology so interesting. The next time you tap, swipe, or zoom on your phone, you're not simply touching a picture. You're interacting with a microscopic electrical grid that's constantly measuring the world above it and turning those tiny changes into commands almost instantly.